you have more data, and that can also be used to get a better estimate of the parameters. We see just with the azeotrope itself, we can determine the parameters. So we looked at the example of benzene and ethanol using the Van model. Ethanol is component 1, benzene is component 2, and it has an azeotrope of T into 1 atmosphere. T is equal to 68.24, and x1 equal to y1 equal to 0.44. We saw this is actually turned out to be a minimum volume azeotrope. We found that the gamma 1 at this point at the azeotrope, gamma 1 and gamma 2 are greater than 1. Right? And this would mean the parameters A and B, the Van model, are both positive, and we calculated them to be we saw that this would mean that the x-escape field is greater than 0, which means that that can also be regarded as a measure of a positive deviation from ideal. We also wanted to how the bubble pressure then would be greater than the corresponding bubble pressure for the ideal case. That can also be regarded as a way of determining whether it's positive or negative deviation. We also said positive deviation means it's more likely the system would exhibit that, not more likely, possible, but how it exhibits an azeotrope, it would be a minimum volume azeotrope. So with this, we can now move to directly to construct the diagram. So if I take E into 16.24, how does the rest of the points look like? Right? So we can easily verify, because here we can calculate the bubble pressure, which is very easy to do. We want the Pxy curve at P equals 68.24. To actually check whether this would actually have a maximum at the azeotrope. If you want to check that, it's very easy to do by simply, if you look at the rest of the endpoints, can be easily calculated from the Anton's equation. So I have here mole fraction of ethanol, which is component 1, and its saturation pressure at 68.4 can be calculated easily from the Anton's equation. If you know how to approximately sketch the curve, and clearly let's say this is 76P, at which it has an azeotrope. So the argument that we made was if it exhibits a minimum volume azeotrope, that means Px and Dy will have a minimum at 1 atmosphere. We can correspondingly show that at the azeotropic temperature, Px and Dy will actually exhibit a maximum. If you know what minimum volume means, and not look at the Px vector but the Px vector to conclude whether it is minimum volume or maximum volume. So now this is 519, and so what we expect the curve to be is approximately like we have a maximum, and we have something like this. And this point will be in the meta look like 0.44. This is again 0.44. This is what we expect. We easily show that easiest way to do it is take the let's say x1 equal to point, I don't know what I have here, x1 equal to 0.3 is what I have. If I take for x1 equal to 0.3, then I can easily calculate the bubble pressure. You can find the corresponding y. So if I do that, then T is clearly P1 sand of T is 68.24. That's common for all the points gamma 1 x1, right? Plus P2 sand gamma 2 times 1 minus x1. So gamma 1, gamma 2. I have now evaluated these points. So taking this gamma 1, gamma 2 is at an azeotrope, right? So given x1 equal to 0.3, now I have to calculate this is 0.3, this is 0.7. I have to go back to the formula for gamma 1 and gamma 2 and calculate that. And I have gamma 1 to be 2.0604 and gamma 2 calculated to be 1.2196, and so the pressure turns out to be 755.01. This itself shows that this is going to be a maximum at 1 atmosphere. So here it's approximately 7, that corresponds to scale 755 roughly. That's the pressure, but you have to know which one it is, because if it is the P versus X, then the P versus X would be above. So this is P versus X. So you have to be very careful when constructing the diagram. Right? Clearly now you expect y to be greater than x or y1 to be greater than x1. Y1 can be easily calculated. P1 sine gamma 1 x1 by P. P1 sine, I have to find out at this temperature which we have already found. Right? P1 satisfied not 3.61. Gamma 1 is what I have found here, 2.0604. x1 is 0.3 divided by 716, and that turns out to be 0.4096. Right? So that is the y1 corresponding to 41 approximately. So what we see here is that they automatically get the P versus y curve also. We saw that for the bubble pressure, if I give you an independent calculation for the new pressure, then it will require an iteration. But if I just want to generate the whole curve, suppose somebody asks you to generate the P versus X and P versus Y curve, now you have a choice. Whether you want to solve the bubble pressure problem or the new pressure problem. Right? So obviously we would choose the bubble pressure because that is directly expressions can be obtained. All you have to do is calculate the gamma and you automatically get the new pressure. Only thing is that we are not fixing the y. Whatever y we are getting, we have to take that, and I can easily construct the P versus y curve also. So this gives a point on the P versus y curve. Same pressure. What is the y? Rather than solving the new pressure problem for various values of y, where in each stage you would require an iterative calculation and calculator, that would be really not a smart thing to do, right? So that you have to understand. So I can consider that. Similarly, you can take another value here to the right of the azeotrope, right? I have taken here x1 to be 0.6, let's say. Right? So again, I have to be very careful where I mark this 0.6. So this one means this is 0.6. And on the pxy curve, x1 equal to 0.6. Right? So then I can calculate now y1 we expect to be less than x1 here because it's the right of the azeotrope. Both on the dxy diagram and the pxy diagram. To the left of the azeotrope we have y greater than x, and to the right it would be less than x when we have a minimum y azeotrope. Right? So that's something, and we can easily verify that in this case that you can do all the calculations. The pressure turns out to be 751 mmHg approximately, and the y1 you can calculate it to be 0.484. Where we get the value to be less matches with what we expect. So what I am trying to point out here is with this pure component property, and this you can approximately construct. You should be without doing any further calculation construct the curve, because we know that this is is 500, this is 500, so 760 would be normally have to go to a maximum. That is why we tell you, even worrying about what gamma is, whether it's positive or negative. So then you can easily infer this to be a positive deviation here. Now the rest of the things simply confirm and give you the quantitative calculations to consider the whole diagram. You know qualitatively how it should look like. So in doing the calculations, clearly I would choose the bubble pressure to do it here because that's the easiest to do. And I automatically get the new pressure curve also. Right? So what I would say as an exercise you're given, you can do it for the Van-Yard model, find the Van-Yard parameters. And just do a couple of these calculations and verify whether you're comfortable with this. Now, to the other type of diagram, so what would be the diagram at T to 760 mm HP? Right. So here again, right, just looking purely at the, now we've got in the temperature versus composition. So we have seen that if I again got the mole fraction of ethanol, right, so we see that the boiling point of ethanol at 1 atmosphere is 78.3 degrees centigrade, and this is 80.1. So clearly we see that this has to undergo a minimum. 16.24 is given to us, so I can roughly construct this as the T versus this now would be T versus point. This would be T versus X. Again, this is 0.44. Doesn't look like that, but anyway. So this much you can draw. Now we have a choice again, either due temperature or bubble temperature. Either case, it has to be an iterative procedure. It is illustrated already, and bubble temperature for the ideal case. Let's just see the due temperature. Calculate. Just give you an outline. You can go ahead and do a few of these iterations yourself. So what I have here is to calculate the due temperature at let's say y equal to 0.3. So I'm at this end and y equal to 0.3, and on this curve I have to mark 0.3. So this is the temperature I want. And I obviously want also the corresponding X. Now in this case, in fact some of you pointed out that Muhammad, I think that for the due temperature, the bubble temperature actually, you have a direct equation in temperature. Why do we need an iterative process? I went and looked at it. Actually I have written it down in my earlier notes, but I found that it was not really helpful much because let's take a look at that. This ideal or non-ideal doesn't matter. So if you want to calculate the bubble temperature, the answer, the point made was we don't know the temperature. We have one equation in the temperature. So pressure is given, right, and X is given for calculating bubble temperature. So one equation is there. Why not? You can solve it, but pressure P1 sand has been written as 10 raised to A1 minus B1 by T plus C1 times X1 plus 10 raised to A2. The anti-equation is not in a form that's very convenient. So you have to solve this. There is also requires an integrated procedure. You cannot get it as I had hinted that you may get a polynomial. It's not going to be possible. You have to logarithm in the saturation pressure. Fine, what you're saying is correct. You get one equation, but you still have to solve the non-linear equation. This still requires an iterative procedure. Right? And you have to solve it using one of the standard non-linear equation solved. That's also perfectly fine. We are not going to follow the standard. There's also some books that are actually given that. And they might have to go again and do an iterative procedure to solve the. But the one I have given is probably more widely discussed algorithm. So we'll just work it out for the due temperature. So here we have again the idea is P1 sand of T gamma 1 x1 and T y2. P2 sand of T gamma 2 x2 is 1 minus x1. Right, so standard to say y is given. So I have to impose a move fraction constraint for x. This is one of those algorithms from Smith and Madness, right? So, and then divide by one of the saturation pressures to get an iterated equation for the temperature. So if I want to do that, I will write first x1 is equal to Py1 by P1 sine gamma 1 and x2 is equal to Py2 by P2 sine gamma 2. Now I will add these and impose, because I don't know x1 or x2. So I am going to apply the move fraction and eliminate x1 and x2. So 1 is equal to P times y1 by P1 sine. So we see that the procedure for this is almost identical to that of the ideal case. Procedure is the same, but you have to now deal with the gamma, which is of course dependent on both x and t. So anyway, we are going to assume an x and t. You calculate the gamma at the assumed value of x and t. So y1 by P1 sine. And you will have in addition, this is the only difference. Anyway, I am going to work with only an assumed value of, I have to assume both temperature, but here I have to assume an x also and calculate gamma 1 for that. Plus y2 by P2 sine 1 over gamma 2. So now our whole idea is to get the ratio of saturation pressure. So here I have to multiply. I can multiply by P2 sine and then I get y1 times P2 sine and this will cancel out. So the final expression is I can write this as P2 sine T of k plus 1. I know I write the algorithm, the iterative formula for the temperature can be written as P times, and P is given to us, P is 760 mm here, right? So this is a view temperature, P is given, and the y1 is also given. So those are known quantities, right? And so P2 sine by P1 sine, this is now going to be a function of temperature, and I have to estimate it at a certain temperature. That would be the previously assumed temperature. And also, gamma 1 would have to be also evaluated at an assumed value of both x and t, plus, and then I have y2 by gamma 2 of x, a, t, j. It's good to have an idea of what the x we know, because we have taken it, because this is an azeotrope is there. So the knowledge of the azeotrope and plotting it qualitatively gives us a good way to choose x. Otherwise, we would know that x here has to be less than 1. Right? So maybe that is not a big issue here. But anyway, even the normal is even without the azeotrope, for instance, we given the bubble temperature. I know that the y that I assume, for let's say x equal to 0.3 I give, the y that I assume clearly has to be less than 0.44 because of the existence of the azeotrope. Right? So I'm looking at this portion. So then I can, now I have to start with the T naught. So T naught I know is certainly somewhere between 68.24 and 80.1. I can sort of see that this is from 0 to 0.44, it varies. I can sort of assume a linear relation and choose a T naught accordingly. Anything you can choose, but that's between these two temperatures. Right? So you can say roughly, if it's 0.3 and this is 0, so between 0 and roughly 0.45. Right? So I want a value at 0.3. Roughly 2/3 of the difference between this can be an assumption. Then we are assuming a certain linear behavior. So I can assume a T naught. Obviously, x naught. So T naught will lie between 16.24 and 80.1. But you can approximately assume it's linear and choose the temperature, or just choose any temperature between the two. clearly x has to be less than 0.2. Yeah, I can maybe choose something, let's say 0.2. Let's say for that anything else. But it has to be less than 0.2, definitely. And T naught anything you can choose, maybe 70, let's say something in between, more towards, I don't know, you can choose anything, 72 or 74 or whatever. And then proceed. So the rest is I let you do the calculation. So anything you choose, right, should be meaningful. Right? And then you just follow the same working that we have done for the ideal case, which we have looked at the bubble temperature calculation. Continuing at each scale to have this additional calculation to do. But here we are not assuming any direct dependence. We have calculated these parameters and assume that these are independent of temperature. The A and B. We don't even have to take that into account. In general, A and B are functions of temperature and that is given. Then you have to take that also into account. Typically, we assume this temperature range is anyway very narrow, 80 to 68.2. Very narrow, so you can pretty much assume that the vanilla or whichever constants you are calculating are independent of temperature. So basically, the only thing is the dependence on x is what is going to dominate in this case. And so that is the only thing. Otherwise, algorithm is very similar to the ideal case, bubble temperature and room temperature, very similar approaches. Are there any questions? Now, can you do it maybe a couple of algorithm iterations and check if it is convergent? Now what I will look at, so we very much then I will now summarize it. I have given some reading assignments, especially from Sandia. He has given a lot of insights on where which models will be applicable and when do you choose a acidity equation model, when you have to go to an equation of state and various ranges of pressures where different models are valid and what kinds of mixing rules are to be used at different pressures and so on. I want you to read that, but I summarize all of that in the next class. But now we go to the next level of complexity, where we say that even for the liquid, we cannot. The main point here is the activity coefficient model includes all calculations with respect to volume. There is no input at all. We don't have to calculate volume, which is one of the major stumbling blocks in the equation of state. So that convenience we have. But what Sanders and others point out is that when you go to higher pressure, very high pressures, you have to have some volumetric input. So the activity coefficient model is sort of applicable basically for low to moderate pressures. When you go to high pressures, near the critical solution temperature and so on, the activity coefficient model cannot be used with accuracy. You have to use the equation of state approach for both the liquid and the vapor. Anyway, we go to high pressure, so ideal gas mixture will break down. Right? So we have seen now an algorithm for where we where is this? The first is summarize. Ideal clearly is that is phi equal to 1 for the vapor and gamma or phi for the liquid. Gamma L is say equal to 1. Gamma I. So it's ideal, right? Approximately this is 4. And so this is low pressure, similar substances for involved. So next we go to IgM and gamma. So this would be continued low pressures and dissimilar substances, which is a reflection of, which is in turn correlated with the non-ideality of the liquid mixture. Then we saw we are going to moderate pressures, where we can no longer assume, this is called the phi gamma, moderate pressures, dissimilar. So you can still take into account the liquid by the activity coefficient model, because the non-ideality has to be taken into account. But we don't have to put the liquid, the equation of state for the liquid calculation, but we have to introduce the fugacity coefficient in the vapor phase. That is a phi gamma approach. So moderate pressure, we cannot treat the no longer the vapor phase as an ideal gas mixture. So you have to calculate the deviation from non-ideality using an equation of state by calculating the fugacity coefficient. We saw an algorithm for the bubble pressure, right? How to do it iteratively, right? Now now we go to the phi approach, where high pressures and the similar substance doesn't matter. If you go to high pressures, very high pressures, anyway the gamma model approach cannot work, the activity coefficients, right? And high pressures for all substances, all types of mixtures. There is the phi, where both the liquid as well as both the vapor as well as the liquid have been treated by an equation of state. However, Samuel points out the familiar van der Waals mixing rules which we have introduced may not always work for many substances which are very dissimilar in nature, and so we may have to use alternate mixing rules, right? So that is where the complication is, but we have to use the equation of state. Now, if you look at the algorithms, they will now start having a very similar algorithm to the algorithm we've already written for the bubble pressure for the phi gamma. If you go and look at it, the way we constructed the algorithm, and I will point out the similarity. Because the bubble pressure is one where for both this and this we got direct explicit expression. So this is the first time we encountered the phi gamma. The bubble pressure also we need an iteration. If you just relook how we did this, we wrote this Py phi I of P1. I just want to point out some elements of the structure of the algorithm which should now help you to construct, because there are so many three other specifications, both the phi gamma and the phi. You cannot be memorizing all these, so you should be able to sit down and work out the algorithm yourself, but that's quite easy to do. You should just look at the way we constructed the algorithm, right, for the phi gamma bubble pressure. I'll just recap that. This was Pi sand of T gamma I of X T Xi. And then on top of it we also have Xj equal to 1 and some more Yj equal to 1. So now the first thing, let's take the bubble pressure, which we have already. The bubble pressure means X is specified, right? And pressure I have to find if X and T are specified. We have to find P and Y. The whole idea is first to write an expression for the Y from the equation. So we wrote, in fact, Yi. So there is a Y contained in this, but we don't worry about it. So Yi equal to Pi sand of T gamma I of X T Xi. And divided by E times phi I of E Py. Now I ask what is it that I don't know. I am going to assume that and substitute it into the right answer. So the algorithm would simply be Yi1, right, is whatever I know I will leave it as it is, because I know that. But whatever I don't know, which is coming in the denominator, so this would simply become, that's all. That will give you the algorithm. But now there are two stages. So now the only difference between this and the phi approach, if you see, is only the way the gamma is now replaced by the phi of the liquid. So I have to actually be clear, this is the vapor. So now I will introduce the now what are the equations? So the procedure is the same. Whichever mole fraction has to be found. So for bubble pressure, Y, right? So for tube pressure, it will be X. So I have to rewrite this whole equation in terms of Xi equal to something. And then construct the working formula to calculate the mole fraction. But that's not all. There's another aspect we will also check the mole fraction constraint. So here, the difference would be Pyi. The right hand side remains the same. The left hand side is going to be, now again, this was also going to be the fugacity of the liquid, the component I in the liquid is also expressed in terms of fugacity coefficient, and the equation of state is not in terms of the activity coefficient model. So here again I have to have Pxi phi I L of Px I equal to 1 to C. So the same approach, I don't know what y is, right? So I'm going to write it. So P can be cancelled here. So yi is going to now look like xi phi I L Px divided by phi I B P y. So now the only difference is that this equation is here different, numerator is different, because I am bringing the liquid phase also by equation of state. So only the equation is different, approach is same. I don't know P and Y, so it will appear here. That's all. Algorithm will be very similar. Now we saw the two aspects to it. The first we will check if yi of j, you can in fact make it j plus 1 if you wait. This can be a general for all iterations. So I start obviously with E naught and y naught. And then first thing I would check is yi minus yij plus 1 minus yij, right, is less than some delta for I equal to 1 to C. Because the first, the inner loop will check only the difference between successive mole fractions of the iteration. We don't check the mole fraction constraint at any point. And it is continuous. And once it has reached, right, if no, then we go back. This now becomes, continuous, right? So the same, the yj plus 1. So if we start with P naught, Y naught, then I will simply put P1, Y1 here and then Y2, right? So if this is now we have reached this, then the next part of the algorithm is the updating the pressure, right? And we saw that PA plus 1 is equal to Pj. Either it has been divided by the sum of the mole fractions or multiplied. Which one was it? The easiest way to remember is that's the second part. The first part is how to write this. The second part is whether we update the pressure or the temperature. Which of the mole fractions have to be checked. That will determine whether we have to multiply or divide. The easiest way is to look at the ideal case. Because this one has Pyi times something is Pxi times something, Pi sat, the ideal case. Just look at it and you will get all the answers. So now, this is actually not the activity question, but the ideal case. The non-ideal case, you are getting some other quantities here. But this will clearly tell you, for instance, if we are now looking at y and updating the pressure, right? So we see how the y's depend on the pressure. So yi, you can clearly see, is inversely proportional to pressure. So that means if the yi is all added to something greater than 1, right? That means I have chosen a lower pressure than what I should have, so I have to increase the pressure. So with that idea, I can simply say that this has to be sum over j equal to 1 to C, j plus 1. Now the same thing will apply here. So only this equation is different. That part of the algorithm remains the same for bubble pressure. Now let's say we go to due pressure, right? So due pressure, again this equation will look different. Now for due pressure, let's just take off, maybe we can take a new temperature and see how it would look like, right? We will look at bubble pressure. Let's take new temperature. I'll just do one of these algorithms. So there are two aspects: how we write the equation to calculate the mole fraction, right? And how you update the temperature or pressure, right? So for that, due temperature, right? So due temperature means what? Y is given, pressure is given, and so we have sort of interchanged the whole thing, right? So this is the analog of that. So x and t have to be determined. So let's say we are working with this, let's say the 5-5 approach or the 5-gamma approach, it doesn't matter. Algorithms are going to look the same. So let's write this, right? So now what I want to find x, right? So I'm going to write this in a slightly different way. So I'll write this as xi is equal to xi is equal to yi times phi ib of tpy divided by phi im of tpx. Here it will be slightly different because of the gamma pi sat times gamma. So now I do want to see. So again I say y and t are given. So t and x are what is not known. So I have to assume them. So I can in fact write this as j plus 1 is equal to dj. So that is one part. Now we will again check whether, for instance, xi j plus 1 minus xi j, the modulus is less than some epsilon or delta or whatever. Now I have to take the temperature, but this has to be done with respect to x. So again I see here, if I just use the ideal as the basis, it seems to give the correct algorithm in each case. It is easy to see the dependence on temperature and pressure, and it seems to apply to the phi as well as for the phi term. So I now look at this and say xi here is given by dy by pi sat of t, and we know that pi sat increases with temperature. So if xi has been greater than 1, let us say, it adds up to greater than 1, that means I have clearly underestimated the temperature. So I need to increase the temperature, right? So I can write this as here the algorithm would be tj plus 1 is equal to tj times I have to increase the temperature, right? Again it would be sum over a equal to 1 to c xj j plus 1. So we can easily see if the sum adds up to greater than 1, right? Then it will increase the temperature. That's one way. You can also look at the other way, what it happens less than 1. Then I have to decrease the temperature, same formula would hold. So you can now easily infer what is going to happen in the two other cases which we haven't discussed. I just look at this part, right? Now for the new pressure, you can easily guess that it is possibly going to be, I'll just put a question mark. This is probably going to be Pj divided by new pressure means y is given, so x has to be determined. This is probably going to be xj. You can check this. The same argument using the ideal equation, whether this is going to work or not. In the other case, the bubble temperature is probably going to be Tj plus 1 is equal to Tj divided by sum over j into 1 to c yj. You can check now both the books and check these algorithms and see if it matches with the outline I have given. So you have to think about it. Of course, you can try to remember that for the bubble pressure I have to divide and for this I have to multiply. But it can be easily inferred by just taking this as the basis and see how we could work there, and it seems to carry over to other algorithms. That's the way algorithms have been constructed. So what I would like you to do, go to YDC or Sandler, look at all the algorithms and try to write out your own equations and your own based on the ideas I've given, and see if it matches with what they have given. And there are some discrepancies and we'll discuss them in the next class. Are there any questions? So this sort of completes the VAE part. We have to look at other aspects of phase equilibrium. So the gas solubility and liquid equilibrium. We take up the next B. Right? So I would just leave it with this assignment. Whatever reading assignment I have given, you should go through because so much information is there. It's difficult to give all of that in the classroom. And anyway, there, you might have to go and just read them. But I have given you the basic idea how to construct these algorithms. If you keep them in mind, rather than just try to memorize one after another. Because there are so many cases we have seen, ideal, VAE, phi gamma, phi phi, and so on, Bobby question, you cannot be expected to memorize all these algorithms. You should be able to sit down, given a particular case that I gave in the quiz, you should be able to first write down the basic equations and construct the algorithm based on that. So, there are no further questions.